Hello everyone, welcome to today's class, Organic Spectroscopic Analysis. In the previous lecture, we have learned about the principles of NMR. Let's recall how to produce NMR phenomena. Firstly, the spin number of the nuclei is not zero. There is an external magnetic field, B0. Radio frequency electromagnetic waves in the vertical direction of B0. When the frequency of the radio frequency electromagnetic wave is the same as the Larmor frequency of the spin nucleus, the nucleus absorbs the energy of the radio frequency wave and transitions from the lower energy state to the higher energy state. Thus, nuclear magnetic resonance occurs. An NMR machine consists of a powerful supercooled magnetic, which is stable with sensitive control, producing a precise magnetic field. Secondly, a radio frequency transmitter emitting a very precise frequency. And detector to measure the emission of radio frequency by the sample, and the recorder to plot the output. The NMR magnet is one of the most expensive components of the nuclear magnetic resonance spectrometer system. Most magnets are of the superconducting type. The NMR magnet is one of superconducting type and has been immersed in liquid helium. It's the most expensive component. The following image is an actual cutaway view of superconducting magnetic. Going from the outside to the magnetic to inside, we can see a vacuum region followed by a liquid nitrogen reservoir. The vacuum region is filled with several layers of reflected matter. The fraction of the matter is to reflect the thermal photons and thus diminish heat from entering the magnet. Within the inside wall of the liquid nitrogen reservoir, we see another vacuum filled with some reflective matter. The liquid helium reservoir comes next. This reservoir causes the superconducting coil of wire. Why should the photon nuclei behave differently in the NMR experiments? The answer to this question lies within the electrons surrounding the proton. Since electrons are charged particles, they move in response to the external magnetic field so as to generate a secondary field that opposites the much stronger applied field. This secondary field shows the nucleus from the applied field. The electron density around each nucleus in a molecule varies according to the types of nuclei and the bonds in the molecule. The opposing field and therefore the effective field at each nucleus will vary. This is called the chemical shift phenomenon. The external field, B0, must increase to compensate for the induced shielding field. As a consequence, the NMR equation need be modified to this format, where sigma is the shielding tensor. The mu0, Larmor frequency of the protons in the electric-rich chemical environment, have bigger sigma B0. When mu0 is unchanged, change B0, called sweep field, the nuclei of different environments in the molecule will have different resonance absorption peaks due to different sigma. Consider the methanol molecule. The resonance frequency of two types of nuclei in this example differ. The difference will depend on the strength of the applied magnetic field B0. The greater the value of B0, the greater the frequency difference. This relationship could make it difficult to compare NMR spectra taken on spectrometers operating at different field strengths. The term chemical shift was developed to avoid this problem. Chemical shift is expressed as the following equation. The location of an NMR signal in a spectrum is to be reported relative to a reference signal from a standard compound added to the sample. Such a reference standard should be chemically unreactive and easily removed from the sample after the measurement. Also, it should give a single sharp NMR signal that does not interfere with the resonances normally observed for an organic compound. Tetramethylsilane, usually referred to as TMS, meets all these characteristics. 12 hydrogens and 4 carbons suffer the same chemical environment and have become the reference compound for the choice of hydrogen and carbon NMR. So today's lecture, we have learned about the NMR instrument and chemical shift. Let's continue to learn more about NMR in the following lectures. Thank you for watching.